So let's work now with iMineralysis. We're going to start working on basically testing what I call the trial and error process of the multimedia analysis. As I said, this is not a software class, so you're going to have, I tried by sending you the how-to guide on working in iMineralysis, basically so we could, you could follow the steps without knowing what to do, like how to use the software and do the exercise. Then also I send you the project that is already set up, so you don't have to set up the constants, you don't have to do all the work that you need to know how to use the software for. We're going to start first with what I call the part A, and I'm going to explain more about this. It's just what I call the forward modeling. The idea is that you're going to run the multimineral analysis, just the forward modeling piece, to obtain a first pass result. With that first pass result, excuse me, we're going to inspect that and adjust and try to adjust the properties of the constituents, in this case, the constants, and run the process again to see how it changes the results. We're going to compare, and then hopefully we have enough time to run that more than once. I'm going to do it first myself. I'm going to show you like do first and these first two bullets so you can see how to do it. I'm going to let you do it. You can start sending questions through the chat. I will answer them while I let you work on your own. And I can do a couple of more tests after that. We're not going to get necessarily to the final solution. We're going to try to get to a decent solution in this part A. Then we're going to do part B, and we're going to talk about that later. But the idea with this is that I want you to feel what happens and how the data, how your changes affects the data fit and also your overall solution and your fluids and your fluid distributions. So let's talk about I would call like the problem that we have. We have here this is a known unconventional reservoir, and I'm going to name it here because the data is not 100% confidential. It's kind of public, but I didn't want it to share the source at this point. So there is no core available for the well. There are no mod logs, and the only thing that I have is the cuttings. The current description sometimes can be useful. In this case, really unreliable. If you see the only description they have is this is 100% shell. And this is actually how we miss so many of the unconventional reservoirs, because they were all described as shell and they didn't describe anything more about them. In one of them, it says 80% shell, 20% limestone. So what I did is I looked for reports, published information from the area, and I got from one publication that this formation is around 40% quartz and silica, so you have the clastics, and you have 35% carbonates. I don't know which mix from this publication, and around 25% of clay. I did find some core data from nearby wells. This nearby was actually several miles away, but it gives me more information about it. And this is really important for you. You may not have the calibration in your well, but you may have something nearby or even a little bit farther, as long as you understand that there are not major changes. So when you look at this data, and I did my own averages here, but you see they actually already like mixed it with the clays here. You have chloride, kaolinite, illite, and a mix of illite and smectite. Your major clay mineral is actually illite. You have carbonates, which I would say like, I call it calcite, but based on the core, you actually had a lot of dolomite and siderite. So here it looks like calcite is more abundant. Here in some samples, in some other ones, it's actually more the dolomite and the siderite. You then have quartz as the more abundant one, and you have feldspars and you have pyrite. And it's interesting to see that they actually mix the pyrite here with the quartz. So I didn't use like this mix completely, but I said, well, we should be, when you look at the two of them, clastic content should be between 34 and 42%, which is consistent with the publication. Carbonates is different here. They actually, in these two samples, they have much more clay, between 45, 56, than in the publication says of 25. So this tells you that we have a lot of uncertainty. It tells you at least which minerals to start from. But when we're going to quantitatively calibrate the results, we have to keep in mind that this is going to be a rough range. We won't be able to know exactly what the number is. We also have, and on the other hand, in one of the wells that have core data, it has also kerogen information. So I have the liquid TOC here. I see that my S1 is not, it's low, but it's not really close to zero, which means that it's definitely not clean. And actually, in this case, it also tells me that it's not a gas reservoir 100%, at least for where this core is located. But after I did my corrections, and doing the corrections, meaning what we did yesterday, that I converted this TOC to weight, and I tried to and converted to fraction of kerogen. My fraction of kerogen based on this well is around 3% average, but the range is between 1.3 to 5.7%. And this is an average, so it's again, just a reference. We know that we're not at 20%, and we're not below 1% kerogen. So what do we have in our matrix? So what I included in the matrix, I included quartz. I call it quartz, but it's definitely clastic that it has to include feldspars. I included calcite. I call it calcite, but it's really the carbonates, and actually it has some, we have to keep in mind that it has dolomite and siderite. We have kerogen, probably high maturity, and the reason is that the well that we're solving for, and you're going to see it in the iMineralysis project, is really deep. We're in the 18,000 feet, around 5,500 meters depth. We have something that I call shell, and that's just I would call it a bad habit from a long time ago. I should probably be calling it clay, but we call it shell. And I see I have a question. I'm going to address it in a minute. And I'm going to call this water. And I'm actually start with gas, independently of what is said in the TOC, because this well is really deep. So I'm going to start with gas, or it's maybe a light hydrocarbon. I know from the area what, I mean, I may know from the area what it produces, but I'm going to start with those assumptions. It says here, the NFI signature of MLIS. What does MLIS, sorry, just didn't come up according to my head. Can you explain what the acronym says? Mixed layer electrolyte can vary greatly depending on expandability. Yes, and how do I account for that? Is a trial and error thing. Is that if you have more, if it's more expandable, I will assume it has more water in the structure, which means that it has lower density, higher neutron, and with the U would be also a lower U, lower PE. So that's how we probably address it. I won't know exactly the properties. I know that we will have to consider that when we're, that's basically what I call the uncertainty on the properties of the clay, and especially when it's a mix, it's going to be high. So when this is going to be what I call our initial matrix, and this is what we're going to try to solve for. So we're going to have kerogen, shell, calcite, quartz, gas, and water. We have the logs that we have the conductivity. I'm going to give you a reminder about this, gamma ray neutron density, the U, and we explicitly put the unity. Not necessarily is needed for that. It's actually already in the background, but we like to put it as a reminder of the number of logs that you can solve for. As a reminder too, the pseudoconductivity is the inverse of the resistivity, but to the N or M square of that. So just to give you like a quick rule of thumb to think about how you, I would call it, change the conductivity of the water, for example. And actually, I want to explain also my nomenclature. The X means that we're in the pseudo, it's a pseudoconductivity, it's not a conductivity only. And the 20 means that I use some M equal N of 2.0. If you see a CX of 18, it means that the M on N is 1.8. It's not going to be relevant for this example, but if you see something from us, sometimes what I do is that we need to pre-process this before we put it into the software. So I calculate the CX 18, 20 or 16 as well, so I can test them quickly without having to go back and redo it. But so a CX20 of 4.5, what it means is that we have a water resistivity of around 0.05. That means that for a temperature of 275 Fahrenheit, we have around 45,000 ppms of of solids, of basic salinity. If the temperature of the reservoir is cooler than that, 200, it will be around 60,000. I didn't have the temperature measurement for this log right at hand when I did this, so I just put you a range. This is a deep well, so we expect that it's hot. And if you change the CX20 from 4.5 to 5.5, that gives you an RW of 0.03, and you are basically increasing the salinity. If you were at 275, you are increasing from 45,000 to 60,000. Keep in mind that a formation like Bakken, for example, has the salinity of that formation is 275,000 ppm. Many of the unconventional reservoirs have high salinity, and it's just to give you kind of a tip that, well, maybe we're starting with a value of RW that is too high. It probably should be lower than that. So if you want to increase the salinity, what you do is that you increase the conductivity here of your water. We also have questions about, does that affect the conductivity of your clays? In theory, I would say no, because in theory, the clays should be, what is inside the clays is fresh water, it's just the water molecules. But we have seen that there is some effect on that. So you can, if you increase this too much, you probably are okay to increase the conductivity of the clays as well. But since there is so much uncertainty about the conductivity of the clay, because we're talking about a mix, you cannot feel free to change the conductivity of the clay if you feel that is relevant to do. So we're gonna quickly do this so we can start the exercise. Let me think about this. Okay, yeah, we're kind of running out of time. No, we're good. Okay, so the trial and error, we need to do the coefficient changes. So this is how the table for the constant for iMineralysis looks like. What I want you to do when you do this exercise is forget about what we call the limits. So we have the limits that we're going to explain how we use in the second part of the exercise. But I want you to focus on the coefficient. The coefficient is basically that number of the constant. So for a moment, when you start using the software, forget about all that and think about the properties. So the table that you saw before is really here. So I'm going to go and open iMineralysis, and I'm going to show you the results. And I'm seeing that we're a little bit behind. So we're going to have to just hurry up later on. And it's okay. I have some material that I can skip quickly. So I'm going to switch to my iMineralysis software. Let me open this here. I'm going to start sharing iMineralysis. Here it is. Okay, hopefully you can see it now. And we're going to, I'm going to open the project that I sent you. And I'm going to do the first tips really quickly. And you can do that as well. So we have your LAS data here. This here. You can click apply. I think we fixed that already. Sometimes it's good to click apply quickly to make sure that the data is selected. You just have to go through the first three things and click apply. So you go to select logs, click apply, go to select samples, and click apply selections. You see here that we already pre-selected the samples that we need for the formation that we're going to use. You're going to go to the setup analysis, click on search limits. This is where we set up the table. If you click only up here, this is what I call the maximum and minimum for each of the constant. I would say forget about that for a minute. Just click on what it says initial. That will give you the coefficients. I think you don't need to click apply here, but let's do it just for make sure everything is fine. And you're going to run the first forward model. To do that, you're going to go to analyze. And sorry that I'm going really quickly. Hopefully you can do that and I can start doing this. So in the analyze section where it says prepare analysis, there is this window here where it says select intervals to analyze. The intervals are already selected for you. It's doing basically all the well, but only in the selected samples. And The search limits is going to be always set initial limits. You can skip that. Let's not think about that for now. And you're going to select your initial startup coefficients. It's important here that don't click on optimize coefficients. We're going to see that in the part B of the exercise. Just click on the forward modeling. And here for result name, let's call it base case, and just click on prepare. So you click on prepare, it's going to do a quick review of your model, and it's going to tell you if you have a big error or not in your model. It should not have an error. And I'm not going to comment right now on these messages because we don't have time. And you just click on start. It should run really quickly and send you to the results window. When you are in the results window, you can see right away that, well, we have a decent data fit, but still you have issues here. In your overall solution, and let me see, I don't know if you can see my mouse. Yes, you can see my mouse here. So in the overall solution, that we do not have much quartz. We have some quartz in the lower part of the section. We should expect some quartz in the upper part. We know that this produces hydrocarbons. We should be in green, and we don't see the hydrocarbons. The kerogen here seems to be high. If you want to see how much kerogen you have to go to this icon here where it says display setup and go where it says kerogen. And I'm also actually going to include the water saturation so we can do QC there and click apply. You can actually look at all the minerals individually, but I'm not going to look at that. I also want to change the scale briefly here for my kerogen and my conductivity so you can see more how it changes. So you go to that icon here that is the circle, and you click on the CX, and I'm going to say I'm going to do that with 1. You have to change that actually every time it shows you results. And with kerogen, I'm going to actually do it. I want to see between 0 and 15%. If you remember, we should be between 0, 1, and 5. So what you can see right away is that definitely we do not have, the water saturation is really high. This is the 1 here. And the kerogen is too high. It's in the 15%. So now you have to start thinking, going back to your setup analysis and think about the constants that you have. For a moment, also ignore the rest of this, I call like matrices that we have, and just use the initial case. The initial case is telling us that, remember that we said, well, we should have a mix of quartz, and we're using a gamma ray coefficient of 0. We know that that's not correct. We have feldspar that gamma ray should be higher. I'm not going to try to change it now because it's going to take us too long. So I'm going to change only, I want to think about kerogen. One of the, I would call like the key characteristic of kerogen is that it has high gamma ray. So for some reason, when you look at the results, I'm going to jump to the results quickly, you see that we're fitting the gamma ray very nicely. But the only 2 minerals in my table right now that have high gamma is the clay or the shell and the kerogen. But we're putting too much kerogen. So it looks like the system is trying to compensate for basically a lack of gamma ray in the constants. And we can say, well, let's change the quartz. You still don't expect to have too much there. I'm going to put a little bit here of gamma ray, and I'm going to put a little bit of calcite. That actually, I'm not even going to, try to change. If I run that, it's not going to change too much the kerogen. So what I'm going to do is I'm actually going to increase my kerogen gamma ray to a large number, to 800. And I'm going to click here, and you have to click apply. A best practice to do this is that I usually make a copy. It's just that to save some time, just do it in the same initial one, so it's going to be easier to compare. And after you make that change, you can go to analyze, go to prepare analysis again. I already have it selected. That's why it saves time. But I'm going to, instead of call it base case, I'm going to call it, let's put it here, increase gamma ray. So I increase gamma ray in several of our minerals. So I click prepare and go to start. So now I have the results. So now you can see that right away, your kerogen volume actually went down. And that made an effect that it started to put in some hydrocarbon. So one thing that we can do here is that we can actually compare. We can see also that the conductivity now is much better. Our phi is not matching as well, but everything starts to matching better. You can compare actually all of them by clicking that icon here and selecting from compare. You can select the increased gamma ray model. I see I have a question, so I'm gonna take some time to answer that. And let me just do this just a minute. You can change here the thickness of that. Okay. So when you're doing the comparison, you have, sorry, I picked the wrong one here. I should have compared to our base case. Okay. So, so you have now the base case that we have here, the increased gamma ray case. You have in green the estimated logs for the base case and the increased one. So you can see that we are improving the match. We are doing what we wanted. We wanted to decrease the amount of kerogen predicted. We're starting to put some oil in the system. So let me read the question from Noga. One of the problems in this type of modeling is that you can't know the answer unless you know the answer. In other words, there can potentially be endless combination of fluid and minerals that you will give you the same synthetic log signature. How can you be at all confident in the result if you have no core data? And again, if you don't have core data, that's when, I mean, depending on what part of the world you are working, you do have some, I would call like, usually you have some knowledge about what you have there. And what I mean by that is that there are publications of your logs. You can, when I did the calibration section yesterday, I tried to talk about, you have the mod logs, you have the cuttings. I mean, there is information about what you have there because you have logs. Also, you can do cross plots to tell you that definitely here you have dolomite and you should not have quartz, for example. I mean, there are ways for you to at least discard which minerals are not present and you should not have there. So it's, as you said, there are infinite combinations, but that infinite combination not necessarily makes sense. If you know that you are in a carbonate platform, you know what to expect, and that's when the geologists can help you with that. You should know more or less what to expect, even if you don't know exactly what minerals are present. And so I'm gonna stop with the questions because we don't have too much time to do the exercise. What I'm gonna want you to do now is that hopefully you can get to this step and quickly actually go back and go to the setup analysis and do another change in the mineral. Just for the sake of this exercise, just go to the initial constant table. You can do the change that I did for 800 and try to do something else. For example, to increase the amount of oil that we are predicting. Okay, and I'll go back. I'm gonna give you 10 minutes, even though we're a little bit behind, but we're probably gonna skip the break since we're doing an exercise and try to explain what kind of a couple of changes that I can do, and then we'll go to the iMineralysis optimization piece, which actually helps with these trial and error steps. Okay, how did I compare the results? If you go to the results section here, the way I did it is that you go to this icon here that is like a pencil and a paper. And when you click, there is an option here to compare. Hopefully you call it differently so you can actually compare between, you have the input, which is the default. You are already comparing to the input. And you can select the previous case, which was the base case. I'm actually going to run a third case now so you can see it and show that. So one thing to remind you is that what we're doing now with iMineralysis is basically the typical workflow that you do in every other petrophysical software that exists that has multi-media analysis. No? So you modify manually the constants and you compare the results. iMineralysis, and that's what I'm going to explain after we discuss this exercise a little bit more. It was created for a different purpose. We actually left this option so we could kind of compare and actually have the opportunity to use it since it's a tool that we use internally. And now we are commercializing as well. to be able to, to use it as a tool for the class, because it's not easy to find, to have demos for all the other software that is commercially available. So this process of coming back to the changing the constants manually, again, is exactly what you do with any other software. And to just also kind of touch base on what Noga said about the infinite combination, that is true, as I said before, but again, you usually know more about the reservoir, and you have to be very, we call conscious of what you use as your minerals. Of course, if you're adding more complex, I don't know, if you are in a granite, in a geothermal reservoir, or if you are in coals, what you have to keep in mind is what makes sense for that formation to have. And also, what is the objective that you're looking for? What we're trying to do is we want to get a better estimate of porosity and saturations, or if you want to know how much calcite or how much quartz you have for a certain reason, or you want to have that as inputs of your mechanical models, there's certain minerals that you don't need to solve for. You just need to know that you have harder minerals. They're all in the carbonate region. So I'm going to go ahead and do a couple of more changes. We're going to work maybe 5 or 10 more minutes with this exercise. And one thing in my experience, for an experienced petrophysicist who works with multimineral analysis, I would say that to tune a model like this, it will take me 2 or 3 days. So I'm giving you only 10 minutes. So I'm not expecting you to get to a final answer doing this manually. I will use the word manually, which is our common workflow. And the process is like that because, as you said, there are too many constants that we can change. And one thing that I have to think about now is like, well, what is the effect of having feldspars in my quartz in the neutron? So should I, I should have premixed it before I put it here. I didn't do it. I used something from a table. This number probably should be higher. The same thing with calcite. We started with 0. It's probably higher because we have siderite and we also have dolomite. So that process of changing, you have to kind of analyze one constant at a time and do a change. And that takes you time. And then you have and change the tolerance. If you have an issue with a normalization, you have to do that. So it takes you 2 or 3 days to tune a model. And that's what you do, the tuning in 2 or 3 wells that are your key wells. It could be more, so it takes you just longer time. I usually tune in 1 well first, then I take a second well and tuning the 2 of them together, and I start adding wells until the tuning is less and less. So the next change that I'm going to do is actually I'm going to change the water conductivity. And why I'm going to change the water conductivity? If I go to the results, I see one of the things that I'm missing is that I'm missing oil. I have, in this case, gas or light hydrocarbon. We have, when we, I would say, like, fix the kerogen, we were able to decrease the amount of kerogen. But if I go to my scale here, I'm going to change that back to 15% so I can see it better. Then it's still like the kerogen, and you can see the number down here. If I'm on top of the blue, we're at 9%, 7%. That's still higher than what the core that I had. We know that in the case of the kerogen in particular, it can be changed a lot in the field, but I know that I need more oil as well. So what I'm going to do is that one thing that I noticed too is that the conductivity is being matched, but it's not perfectly matched. So I'm going to change the conductivity of the water. I'm going to go ahead and that's what I emphasized that when we were in the PowerPoint, that the conductivity of the water should be, could be higher. We're in the deep unconventional reservoir. So I'm going to go ahead and change that to that 5.5. I'm going to actually do it twice. I'm going to change it to a higher value later on. And you click apply, go to analyze, prepare analysis. I'm going to keep the forward modeling option. And I'm going to put up option here. Let's do just water salinity. It actually has the 2 changes. It has the kerogen and the water salinity. And just you should come up with a nomenclature that is more consistent for you to track down your changes. I'm just doing this for the purpose of going with this quickly. So now what we have here is the comparison of the base case, which is the one that we had as comparison, and the water salinity. I'm actually going to change it to the one that had the kerogen change, which was the increases in gamma ray. And it actually looks that I didn't apply, so the changes are minimal in water saturation. Actually, yeah, no, this is pretty good. Let me go change the kerogen. Sorry, I'm in the wrong one. Kerogen. I'm probably going to, hopefully we can get this different, that we don't have to change this every time. But, okay, so you see here that there is no difference for the kerogen when I change the water saturation, but I was able to decrease the water saturation by increasing the water resistivity. Sorry, by decreasing the water resistivity. And this is common. That's what you do in any water saturation equation. So you have to be careful on, like that, whatever changes you make have to be consistent. And what I mean by consistent is that I didn't have, again, from publication in my case, how much salinity could the water be. If you have salinity information, you can change that water conductivity a little bit, but you cannot change it just to fit that, well, I want this to produce oil. No, that's not what that the intention with this is. You have to put a number there that make geological sense. One other thing that we notice here is that we do not have enough quartz. We had quartz in the solution, and that's a more tricky thing to do. So I'm going to try some changes here. I actually don't recall which changes will help me with that. So that's something that we can try to do. We're going to probably not do much. I'm going to change the neutron a little bit here to 0.1. I'm going to change the calcite neutron to 0.1 as well. And that's probably not going to be enough. Let me make sure this is fine. I did a big change before. So this is probably not going to change enough, but I'm also going to, for example, increase the weight of the neutron log. So I'm changing here the tolerance. By the way, if you are changing the tolerance, it's very common to kind of touching one of the inequality signs here, and that will turn purple. So if that turns purple, that's wrong. Go back and change it back to the equal sign. And I'm going to click apply and see if that has an effect on my results. So we're going to go here again, and I'm going to call it tolerance and phi. So I know that I changed properties for the phi and the tolerance. And as you said, these are really small changes. And you saw that there was a small effect. And let's see, let me change the comparison again. So we're going to compare now to the water salinity one. It's probably better just to change the number. This was probably a bad way to put it here. And you see that you start having changes, but they are not very big. The quartz is still not increasing. So the changes in Phi did not change the quartz. So we have to think next about the density. And as I said, this process is manually tedious, I would say, and that's why it takes long time. There are some changes that are going to be easier than others. We can see that the mathematical solution is getting better. If I change, let me see, I'm going to remove the comparison for a minute here. And you can see that actually our conductivity got like screwed up a little bit. And that's probably because it's trying to fit the Phi more and the conductivity less. So you can now, for example, increase the conductivity tolerance, so it can try to fit the tolerance more. You can also think about, well, maybe you don't trust your PE too much. You can loosen up this tolerance here. So what we're going to do now is that this is what we call a trial and error. We're going to do now, and I'm going to go back to the PowerPoint, and I'm going to explain you what we did with iMineralysis. And what happened is that this trial and error process was, again, difficult. So internally, like 15 years ago, we started talking about what options we have with petrophysical models. And as I said, we created this tool, and that is going to help us with this piece of the trial and error. So it's basically the same multimineral solution. It's just that it kind of helps us as users in that process of trial and error. So I'm going to, unless there is a question about this, I'm going to change. As I said, we are not able to run everything. So until we are, until the end. of the solution because of lack of time. But let me go back to my PowerPoint. I had a quick break here, but I'm gonna skip it so we can finish with the material. And let me go here, new share. And we're gonna go back to the iMineralysis software. So I will demonstrate this piece, and I'm gonna let you, if we have time, I'm gonna let you 5 minutes to just run the optimization yourself as well. So what we call the alternative method here to accelerate the process and improve accuracy is just that what we did is, and I'm going to skip few slides here. You have them in the material that I sent, and that I'm going to send again with the correction. But you should, if you want to know more about it, you can go there. I explained this as what I call our flow process or a workflow process of what is the multimineral analysis. We start with the constants, we estimate the volumes and the logs, we compare them. If whenever they're ready, we're done. If not, we just have to keep manually adjusting. So this is an iterative process. From those processes, there are basically a lot of them that are manually done. So what we try to do with iMineralysis, we say, well, let's use some artificial intelligence. And in this case, what we used was a genetic algorithm to try to help with some of those manual pieces. So what we're going to do is that we're going to try to replace this inspection of the real and model logs and do the adjustment. Instead of doing it manually, we're going to try to do the adjustments automatically using the genetic algorithm. So the generation of the next, I would call it trial, is going to be done by the algorithm. And the genetic algorithm, it doesn't find what we call like the perfect and the more optimal solution. It just goes through the process several times, finding each time a better and a better solution. So we end up, again, it's imagine that it's yourself doing this, and you know that the density of the quarks can be between 264 and, or actually maybe 262 and 267 because you have feldspats. So you go, imagine that you do that and try to go to certain combination. It doesn't, the algorithm doesn't go what we call exhaustively, testing all the combination. It just tests a combination, picks a good one, keeps that, and keeps going. So I have some slides about that I'm not going to go now, about what a genetic algorithm is and how it is explained basically for the multimineral analysis. But this is how the workflow looks like after we introduce the genetic algorithm. So instead of starting with one set of constants, it's going to actually create as many as, whatever number you select in your, what we call individuals, as your starting point. It's going to select that between those limits, the ones that I told you to ignore. So it's going to pick numbers from within those limits for each of your constants, and it's going to run the model. So it's going to go ahead, create an n number of sets. It's going to create an n number of model logs. It's going to then calculate an error. And one thing to keep in mind here is that this error is different from the one that I talked about before in what we call the objective function of the multimineral analysis. This error is like you with this iMineralysis optimization tool, you're going to have two different errors. You have one that is the one that we solve depth by depth, and this one is actually for all depth. So every time you have a model, if that model is 1,000 feet, it's going to compare an error between the model logs and the calculated logs for each of the depths, and it's going to add them up. And that's going to be now what we're trying to minimize in this, what I would call is kind of like an exterior loop. So you have the interior loop of the solving for the volumes, and then this one to kind of help you to basically select your constants. So it's going to do that for as many iterations you requested. It's not going to end saying that, you don't tell it that I want to minimize the error to a certain number. You just say, I want to run this 1,000 times. I want to run it 40 times. And then it's when we as users start the comparison. So basically what we're trying to do is accelerating the process, especially that the first part that is usually a lot of combination that you can have with small changes in the constant, because the different tables from different publications have different properties of the calcite and so on. So I'm gonna jump here quickly and just go back to the table that we had before. I don't have the arrows here. But what we do in this case is, again, it's slightly different. Now it's actually completely unique for this software, because I have researched this and no other software has it. But basically what we are doing now is that instead of setting up the coefficient, or I would say like only the coefficient, it is actually much more important now to set up the minimum and the maximum. And why I say that is because either the software is going to start, one of the, I would call like the test that it's going to do is going to be that coefficient that we set up. But all the other combination that it's going to test is just it's going to take those coefficients only once. Then after that, it's going to just go and look inside those minimum and maximum limits. And in the results, and I'm going to show you now when we do this live, is that besides the initial matrix of minerals that we have, it's going to give you the final matrix. So it's going to show you that, for example, the shell starting in 0.2, the conductivity, it adjusted that to 0.27. The water conductivity, and this example here, by the way, is not the one from the class, I think. I don't recall now, but it started in 4.5 and they're all in 5.8. One thing that we as users then have to do is that we have to inspect this final metrics and then evaluate if it makes sense or not. So we see that, like you change the calcite to 2.7, it's almost 2.71, that is reasonable. The quartz is heavy, is 2.67. Well, that actually is reasonable still, because if you have pyrite in the system, but you need to know that you have pyrite, because if you don't have that, then 267 for quartz doesn't make sense, and you have to, like lower the maximum limit on your constant. As Noga said, this is a highly non-unique problem. So you, as user, have to make sure that you give it reasonable limits to get a reasonable solution. And it also gives you, this is just a change, basically a matrix telling you how much each of the constants change. So I'm gonna, basically the difference with iMineralysis to any other forward modeling is that you get two outputs from the forward modeling. You get the volumes of minerals and fluids and the model logs. In this case, you have three, which is the same ones that you have with the forward modeling, plus the new properties of the constituents. I'm gonna skip the potential applications. This is something that you can read about. I mean, like the fact that we can do this faster allows us to do more analysis. So we have, I think in the reference, there is a paper about that, and you can think about that a little bit better, no? Especially when you have the kerogen, the uncertainty in the kerogen properties. So with this, I'm gonna now, I'm gonna skip all this and go to the second part of the exercise. So what I would like you to do is that now that you understand what that optimization button does, what I want you is to run the optimization. And actually, instead of showing, I'm gonna show you how to get there, and I'm not gonna run it live. I want you to see the effect of that. And basically, what it's gonna do is that all the things that all the changes that you're gonna do it quickly with one optimization. I'm gonna switch to the iMineralysis software now. Hopefully should be there too, okay? And we're hearing the results. So we're gonna go to the setup analysis. You really here, you don't have to change anything. I already had some limits that make sense for this problem. And actually, there are some that maybe they are too large, and after you get the result, you have to go back and confirm that they should be correct. Well, the difference is gonna go here. When you set prepare analysis, instead of using that forward model logs option, you should use the optimize coefficients option. What happened is that we decided to actually add these forward model logs because for the users that are used to the typical software of multimedia analysis, they wanted to test like, okay, this is what I did in my geolog. and I want to know how it looks in iMineralysis. So they just enter the constant like we did before, and you run this option, and you should get not a very similar solution that you get with any other any other software. But when we use it internally for our consulting job, we just use the optimized coefficients option. I'm gonna change it. You can change it to 40 and 5. You can change any of the two. It's still pretty fast because remember what it's doing now is gonna test 40 generations multiplied by 5. So it's gonna test 200 constants. So the thing that we did before is gonna do it 200 times this way. If you had the default, it's gonna be 2,000 times. It's not too long anyways. I just changed this to the optimization, and click on prepare and just run it yourself. Okay, so I'm gonna press start. Hopefully you had the chance to do it. And it runs the optimization, and you can see now that the results are pretty different than before. You can also see that the comparison between the model logs and the real data is pretty tight. You have some difference here at the bottom, and that basically is something that happens with this tool because you are running the model so many times that it, of course, finds one that is better than the rest. And the idea of running this, it has to fall, yeah, this is what iMineralysis does, but this was the best way to show you what happens when you are in any multimineral software and you spend several days going back and forth changing the constants. You should get to something like this. Again, iMineralysis tries to accelerate that, and you as a user just help the software. But after a week of work, you should be able to get to something like this. There are things about this the solution that we still need to correct. We need to make sure that the amount of quartz is the correct one. I changed some tolerances, and I can actually do that back. So what happens with this is that since iMineralysis is changing so much the results, and let me show you one more thing here. Since it's already getting you a very good result, especially it's going to give you an excellent mathematical solution and hopefully a better geological one, but you still need sometimes to improve the geological one. Here where it says coefficients and where it has those 3 tables that I mentioned before, where you can compare, this was the metrics, and this is the final one. And you can see what did it do. So it increased a little bit the ρB of the kerogen. It actually decreased the density of the quartz, which is actually consistent with having feldspars in the reservoir. So if you want to start, for example, and run a forward model using the optimized constant that you just obtained, you just go to the optimization, optimize all, and you can see it. This is basically the result of the model that we ran, and you can see the model here. That's what as a user, we will never choose a gamma ray that is 1293.02, but the software, of course, allows to just start checking those numbers.